just gonna be like 6,
All right.
probably
So
6 to 8.
yeah. So welcome to the first day on dynamic programming, and I'll be your lecturer for the first half. So yeah, this is the first day on dynamic programming, and today we'll be covering a few important problems in dynamic programming, including grid paths, the coin change problem, some tree dynamic programs, and then interval DP. And we'll also be covering an important topic in DP called modular arithmetic. So the first problem you'll be introduced to is the grid paths problem. So the basics of the problem is so. You have an n by m grid, and in this grid, you have obstacles. And you're tasked with counting the number of paths that reach from the top left cell to the bottom right. And one important thing to note is that paths can only step either right or down. And if you're approaching this problem trying to figure out an algorithm, one useful thing to note is that if you look at this, paths can only approach from either the top cell or the left cell. So one way to split this into a simpler problem is instead of just counting the number of paths that reach a cell, you can instead count the number of paths that reach the top cell and the number of paths that reach the left cell. And if you have that result, you can just sum those two together to get your answer. And that motivates this algorithm. So one important thing to note is the base case. So in the base case, you just have the top left cell. And the top left cell only has one path that can reach to it. And that's the path that starts at the left and then just immediately ends. And then from here, you can just calculate. So for the rightmost, for the second cell, you can say that, well, there isn't a top cell to look at, so we can say no paths approach from there, and we can just look at the left cell. And from here, we know that only one path reaches the left cell, so that means only one path reaches the current cell. So, for example, what would be the next cell? Great attendance. Well, it's just one. I will be asking you that, just letting you know. And again, it will just be one for the next. And for the next case, well, there isn't a left cell to look at, but there is a top one. And again, we know that at this top cell, there's only one path that reaches it. And because of that, only one path reaches this current cell. One important thing to note are obstacles, which make this problem actually interesting. So here, we say that no paths reach this cell. And that makes sense because no paths can enter an obstacle or pass through it. So we can just represent this by saying no paths reach the obstacle and just put a 0. And then here, well, a path can't come from the obstacle because we said 0 paths reached it. So we just say that the only path that reaches it is the path that comes from the top, and we know there's only one of those, so we can just put a 1 there. And again, for this cell, the similar thing happens. But now there is a left and a top cell. And because of that, there's actually 2 cells you have to count from. There's one path that approaches from the top, and we've already calculated that. And there's one path that approaches from the left, and we've calculated that as well. So that we know just the values too. And you can reach through this, and here's where I'm going to ask. So for this cell, the next one, what's the value? Well, 2, crazy, yeah. I think you guys are right. Well, you guys are right, crazy. And now we pretty much did almost all the work. We only have one more cell. And here, we know that there's 2 paths that approach from the top and 2 paths that approach from the left. So our answer is 4, and we are finished. And to actually implement this algorithm, it looks similar to this. There's a pretty common pattern that you see in many competitive programming submissions, and that's how you actually read the input. And this is pretty common for most of the problems you will solve if you try to go into more of this. And there's many parts that are very similar to the table that we filled out. So initially you have the base case. And here we're going to say that the top left cell has a value of 1, and that will just always be true. And from there, we say no obstacles can be reached by any paths. So if we detect the obstacle, which we denote by a hashtag in this particular problem, we just leave the value 0 and continue on. And that's pretty much how you would do grid paths. And dynamic programming is very similar to this. So let's skip this. So at a high level, so in a problem, you may be able to break it down into simpler subproblems that are almost identical. And if you come across a problem like this, it's usually where dynamic programming comes into play. So in dynamic programming, we have multiple terms we use. We have a state, transition, and base case. The state, as you saw, was sort of like this grid, where we have different integers. And these integers, in our case, were just the number of paths that reach each cell. The transition is pretty much how we denote the rule that we use to actually update the state. In the case of grid paths, this rule was given that we had two cells, the left and the top one, we just summed the value to get the next cell. And then the base case was just that we had a 1 in the top left cell. So if you were to actually have a formal definition of our grid paths problem, it would look somewhat like this, where we have a 2D array, which is the state, and at each element of the state represents the number of paths that can reach the I and j cell. And then we have a transition, and in this case, it's just how you update it. So you sum the left cell and the top cell. And then the base case is just the top left cell is 1. So another problem we'll look at is the coin change problem. And it goes like this. You're given an array of coin values. So for example, you may have a 0, 1, 2, and a 3. And then you're also given a sum that you want to actually get to. And the question is, how many ways can you combine these coin values to get to the sum? So in this case, for example, we see that if you want to sum to 3, there's 4 ways to combine these coins. And another way to break these into smaller subproblems is to say, how many ways can we get to the target sum if we take a coin and if we don't? And since we can pretty much just sum these 2 ways. So for example, if we don't take the 4th coin, it's just how many ways can we sum to 7 while only using the first 4 coins. But if we do take the 4 value coin, then it's just the number of ways for the previous coins to sum to 3. And then we can just add on the 4th coin. And you can see that this is pretty much just our transition rule. And this motivates this table-like algorithm, where first we have a base case, where we say we have no coins. And intuitively makes sense. Because if you have no coins, you can really only get a sum of 0. So we just put a 1 there, and then the rest are 0. And you can see our transition goes similar to this. We can still get to a sum of 0 if we have only one value coin. And that's just if we don't take it. But what's interesting is that if you want to get to a sum of 1. To get to a sum of 1, we can actually get to this by taking no coins and taking the 1 value coin, for example. And that looks like updating it like this in the implementation. And again, you can go through this process, then you get a 0, and then you have zeros for the rest. And if you add a second 1 value coin, you can still get to a sum of 0 by just not adding it. But now you can get to a sum of 1 by either not taking the first coin and then taking the second 1 value coin, or taking the 1 value coin first and then not taking the second 1 value coin. And I'll ask again, so what would be the next value here, or the cell after this? That's correct. It'll be 1, because you could just take both 1 value coins. Thank you for your cooperation. And you can just follow the same process. You get zeros for the rest. And here, we say, well, to get to a sum of 0 or 1, you can't add the 2 value coin. So you just pass down the previous row's results. But also, for here, you can either take no coins and take the 2 value coin, or just take the 2 1 value coins. And that's represented by going back 2, and then you can just see that there's like a sum of 0 here. And then you can follow this process down. You got 2, 1, and then zeros. And then a similar process happens for 3. And you can go through adding up all the results. And eventually, if you continue this process, you'll finally get to the end of the table. And by the definition of our problem, the last right cell is our result. And that's pretty much just, given that you have these 5 value coins, what's the number of ways you can get to a sum of 7? And in this case, it's 4, in case you didn't know. So one thing to notice is that at any given point, we only need 2 rows. So pretty much these top 2 rows in this example are living rent-free. We do not need them, and they are just taking up additional space. So yeah, you only use 2 at a time. The current row only relies on the previous row. And that motivates actual optimization. And that's here. So instead of storing the entire table, you just store the 2 rows you're looking at. And given the first row that's above the current row, you can just update that row and then pass it on to be the new top row, and then go on. And I'll pass it on to Richard for modular arithmetic.
Cool, thanks. All right, so you guys have probably already seen these operations before, but maybe not on these in this context. So as a refresher, like when you do like 8% b in your code, it's taking like the remainder when you divide 8 by b. And here are some examples. Like if you divide 13 by 8, you get 1 with a remainder of 5. And like there's a subtle property which is actually like very powerful, where if you do any operation, not any operation, but if you do like plus or times, and you do 2 numbers and want to take the result modulo a third number, you can first take modulo inside. So like take A modulo C and B modulo C, and then sum those 2 things, and then take modulo C again. And we have an example here. So like you could, if you had 2 numbers 28 and 23, you could like sum them and get 51 and take modulo 10, or you could take 28 modulo 10 and 23 modulo 10, and then get 8 and 3 and then sum those. So this is like a very simple example. This gets like more important when you have like really large numbers. So you guys might have seen this trick before where like there's a math problem and it's like compute the last digit of this big product. And then the trick is that you can just look at the last digit of each of the numbers. So instead of computing 343 times 109 and getting 37,000 something, and then looking at the last digit, what you can instead do is take modulo 10 first for each of those numbers. So 343 modulo 10 is 3, and then 109 modulo 10 is 9. And then you get this small number, 3 times 9, and then you can just compute modulo 10. And so this computation is much simpler for us humans. And also, for the computer, it's also much faster. So in Python, you'll have like, if you have really large numbers, the code will work, but it'll be much slower because it has to like store these huge numbers in its memory. And in C++, it actually won't let you store really large numbers, so it's even more important there. And so this like connects back to dynamic programming, where like if we have some problem where it asks you to compute something really large, let's say like the Fibonacci number. So like if you ask for like the 999th Fibonacci number, and that's like a 47-digit number, it doesn't even fit inside like an integer in C++. And so it'll instead ask you compute the answer modulo like something, let's say like 1 billion. And what that will do is like it'll make sure that the answer that you output is always like length is always like less than 1 billion, because after you take modulo it becomes small. So and then like whenever you see these types of problems, like you might have like implicitly been like just taking the modulo every time you like add 2 numbers. And we have an example here. So like in grid paths, well, the solution we showed last time might not actually work if you were to implement it the way we did before. But this like simple modification will just like help you do it. So when we're like computing the sum of 2 path counts, instead of like computing the sum and then like printing the answer at the very end, we can like at intermediate steps. And here like our intermediate steps is like inside the for loop, we can take a modulo. And we're implicitly using this property of modulo, that like the sum of 2 things, modulo C, is we can take like modulo first. And like the intermediate values here are like each of the path counts in the array. So yeah, does anyone have questions on that? Good. Okay. Yeah, and now like we'll go to another counting problem which does use modulo, which is on a tree. So yeah, before we saw something on a grid, and now we'll look at a tree. So now we have a tree with n nodes, and we're gonna color every node either red or green, with one restriction, and that's that if we put two red colors next to each other, that's illegal. So that's our drawing over here. You can put a green next to a green, you can put a green next to a red, but red is bad. Yeah, and here's an example of a tree, and here's like one coloring of it, where we have like, if you notice, like we have two greens next to each other, we have a red and a green next to each other, but we don't have two reds next to each other. So why can't we just like find all colorings and then just output that? Like, why can't we just like try all possible colorings and then just check whether they satisfy the condition? Yes.
2 to n colorings.
Yeah. So if you do that, like it'd be 2 to the power of n colorings, and you can see that by like there's 2 ways to color each of the nodes, and so the total number of ways to color everything, ignoring the restriction, would be 2 to the power of n, and then that's way too slow. So instead, we'll use something else, and if we remember earlier, like the notion of states, here our state is like for every subtree, and so we have an example here. Let's say like we're looking at this tree, and then we're looking at the root. First look at the root, and then consider like it's either red or green, and so just consider those two cases separately. Let's say it's red, then each of its children must be green. Does everyone see why? Yeah, it's because if they're red, then we would violate the condition of two reds next to each other. But if we have a green at the top, then we just have no restriction. So they can just be either red or green, and that's why you have a red-green like double coloring on those nodes. And so an important property here that we've said here is that subtrees are independent of each other. And what that means is like if we were to color, so these gray things over here are the different subtrees that are just underneath like the root node. And by independent, we mean that if we color each of these subtrees, and like as long as those are legal colorings, then like the entire thing is illegal coloring. So this kind of like, so these two things together like kind of motivate an idea, which is like, let's look at every subtree and then like make the root, fix it at either green or red, and then compute the number of ways to color those. Yeah, does anyone see why it has to be a tree? Like, what if it wasn't a tree? Then would something like this still work? As an example, let's say there's just like one edge here, like looking somewhere over here. Could we just, would anything be wrong about what we just said? Yeah. Yeah, they wouldn't be independent of each other. It's because if we have like an edge there, then like we might have a valid coloring for the left, we might have a valid coloring for the right, but then like we might have put a red and a red next to each other at that very connection that was just there. And that's like why it being a tree is very important here. Yeah, and now we'll go into more detail about what we just said. So we have an example tree over here where let's say the top node has to be red. This is the first case. And so over here we have a tree where the top node is red, and then as we said before, the children have to be green. And then we have an example color. And for each of the subtrees, we have like different possibilities for what it could be. So for the leftmost subtree, there's like actually 4 different ways, and I've drawn those up on the left. And then similarly for the middle one, there's 3 possibilities. One of them we drew is illegal because it has 2 reds next to each other. And then on the right, we have 2 possibilities. Yeah, and the idea of what we said earlier is that like we can choose a legal coloring for each of the subtrees and then combine them all up into one big coloring. And so here we've chosen the circled ones, and then they combine to form the coloring for the entire tree. And this is like essentially what a lot of tree dynamic programming problems will be like, is that you'll have a solution for each of the subtrees, and then you can combine them all into a valid solution for the entire tree. And so here we kind of also see at the same time that the number of ways to color the top tree is the product of the number of ways to color each subtree. Does anyone see why? Like here would be 4 times 3 times 2. Oh yeah.
It's like kind of related to how they're all independent of each other. So you can just multiply each other.
Yeah. So it's because the choices we make are independent, and what that means is that like for any of the choices you make on the right, of which there are 4, you can make any choice in the middle, and you can make any choice over there. So like there's number of ways to choose the first thing, and then you can imagine like doing a for loop through all the ways, and the outermost layer is length 4, and then length 3, and length 2. And then now that was like when the top node is red. Now let's look at the top node as green. And remember here, like those nodes can be either red or green. It doesn't actually complicate things much because if we had the number of ways to color each of the subtrees for either red or green, then we could just sum those 2. And then we get the number of possibilities for each subtree. And then again, same trick here. We just can compute the product of those. So and now we have our entire solution. And so for the leaves of our tree, this is the base case that we saw earlier. So base case here is for a node, it's just by itself. And so it can be either red or green. There's no restrictions there. And then here in our code, we have like each of the 2 ways. So like green is like number of ways to paint where the root node has to be green, and then somebody for red. And what we have here is like we're going and recursing into a child to first compute the number of ways for that child, and it'll recursively compute that, and that gets us our like C green and C red values. And then for red, we're computing just the product of the number of ways to color each thing as green. So that's the last piece of that's the last statement inside the for loop there, and it corresponds to this drawing. So we compute the product of all those, and then for the top node is green, we can just compute the product of all sums of green and red. Does anyone have any questions on this? And there's a lot of times when you're doing dynamic programming on a tree, you're actually doing a DFS at the same time. And the reason for that is like a DFS is a nice way to recursively compute a value based on the values underneath it. If you remember for like computing the subtree size, that's like a simple dynamic programming. You could think of it. So like you compute the subtree sizes of each of the children, and then you sum them to get subtree size of the current node, and then you return, and your DFS goes up and down. And now for our last topic, which is intervals.
Okay, so today we will be doing one more example problem about dynamic programming. So consider the following problem. You have n slimes in a row. Each slime has a different size represented by an integer. And in one operation, we can take 2 adjacent slimes and merge them together into one larger slime. And the cost of this operation is just equal to the size of the larger slime, which is equal to like the sum of the sizes of the two smaller slimes. And then the problem is just asking what is the minimum cost to merge all of the slimes into one. And the number of slimes is actually relatively small. It can only be at most 400. Okay. So one way you might approach this problem that has nothing to do with dynamic programming would be to just try like a greedy approach, because it's not obvious, because that seems like it might possibly work. For example, what if we just at every point in time we just try to merge the two adjacent slimes with the smallest sum? So for example, in this case we would try to merge the 1 and the 4 first, which gives us a 5, and then we merge the 4 and the 5, which gives us a 9, and the total cost of this is 5 plus 9, which is 14. And for this specific sample, that is in fact optimal. Like really, there's the only other way you could solve the problem is to merge the two size 4 slimes first, and then merge those with the 1. But then the cost of that would be like 4 plus 4 is 8, and then 8 plus 1 is 9, so 8 plus 9 is 17, which is worse. So this is like a possible approach that you might think of if you just see this problem. But is this actually correct? Do we have any way of proving that it's correct? Anyone have an idea? No? Okay, well that's good, because it turns out that this solution is not always correct. Wait, can I click OK here, or does that cause bad things to happen? That's okay. So, for example, consider, is my screen still shared?
Yes.
Okay, cool. So consider this case when we have 4 slimes, and the 2 outer ones have size 5, and the 2 inner ones have size 4. So the greedy algorithm I described earlier would try to merge the 2 smaller ones into a size 8 slime, and then just merge them to the side in like an arbitrary order. So the cost of this would be 8 plus 13 plus 18, because those are like the size of the slimes that we merge into. And so the total cost of that is 39. However, this is not actually optimal. In this case, it's better to merge the 2 like outer pairs of slimes first, and then combine them into a bigger slime like this. And this only gets a cost of 36, which is smaller than 39. So the greedy strategy is just wrong, and there is actually no easy way that I know of to fix it. So we need to come up with a different strategy, and it will involve dynamic programming. So when we are doing a dynamic programming problem, one of the first things we want to do is like, let's say we decide that we want to solve the problem with dynamic programming for whatever reason. The first thing we want to do is we want to come up with the state for our dynamic program. Does anyone have an idea of like what kind of state I could use for this problem? How can I break down this problem into smaller subproblems that are also like identical to the original problem? Yes?
What if we consider, like, we'll merge particular pair, and we'll consider all the pairs, consecutive pairs in the array, and then we'll do like merge the first pair, and then do a DP for all the last pairs, and just we sum up with DP for every like slime that left.
What do you mean for each pair? Just like for every pair of adjacent slimes we store something?
In an array, yeah, for example, if we have an array, we will consider first pair, then second pair.
So like first we would consider this, and then we would consider this, and then this?
Yeah. But it would be slow.
Well, this is kind of going in the correct direction, but like if we have a big array, maybe I add some numbers at the end, and the only things we have computed are these pairs. How do we use these values to compute the value of the entire array? So right, that is like another property our state has to satisfy. There must be some way to use like the smaller subproblems to compute the answer to the larger subproblem. So if the only things we compute are the cost of all of these pairs of like subarrays of length 2, this isn't quite enough for us to like find a way to efficiently compute the size of the entire array. Because like once we have computed these pairs, what do we do afterwards?
Oh,
Or-
and then
yeah.
like, so I meant that the subproblem will be, so for example, we merge 5 and 4, then I do recursion and say merging 5 and 4, this will be cost like 9 plus dp of the left.
Of like this?
Yeah.
Ah.
But like we will
Yeah.
need to repeat that for every pair because we need to consider whether we should merge first step should merge like whatever pair.
Yes. Okay. Yes. So this is actually very close to the solution I had in mind. It's basically the same but phrased slightly differently. So okay. Okay. So you basically got the solution, I think. But I will try to explain it in a slightly different way. So the way I would phrase this is, so one thing we have to notice is that whenever we merge some slimes, for example, let's say we merge these 3 slimes, then like the new slime we get for them occupies like one consecutive subarray of our array, right? So then it kind of like corresponds to that range in the subarray. So then what we will have is our state will be like, we will compute for every subarray the minimum cost to merge all of the slimes in that subarray. Actually, yeah, I can do it on the board. So for example, in this case, for the subarray from the 4 to the 6, the DP state would be like the minimum cost to merge all 3 of these, and the optimal way to do that is to merge 4 and 5 first, and then 6. So that would be like 9 plus 6 is, 9 plus 9 plus 6 is 9 plus 15, which is 24. And like, the idea behind this is that if we want to make a slime, if we want to like merge all the slimes from L to R into one single larger slime, then there must have been some like midpoint M such that we already merge everything from L to M and M to R. So, for example, if we have this array and we said that somehow we merge all of these into one big slime, that must mean there must have been like some cutting midpoint such that first we merged everything on the left into one slime, and then we merged everything on the right into one slime. So this was this is quite similar to the idea that she was saying earlier, where you try to merge one pair and then you recurse on like the right subinterval and the left subinterval. But it's slightly different because we don't restrict these ranges to have like length 2 basically. Yeah, so our DP state will be for like every range from L to R. We will store the minimum cost to make the slime for L to R, and then okay. So now we have the DP state. Does anyone want to tell me what will be that transition? So that's usually how we solve DP problems. We first come up with a DP state, and then we try to come up with a transition for them. If we can't come up with a transition, maybe our DP state isn't useful and we try to find a different one. But in this case, I can tell you that this is in fact the DP state I want to use. So can someone tell me how should I write that transition function? Let's say I have already computed, yeah?
That's right. dp lr equals to min, like for all m of sum of l m and dp lm and dp mr.
Okay, that's almost correct, but that doesn't account for actually doing like the final merge. Like that will get the cost of merging these times into one and these times into one, but then we still need like one final step to merge the two slimes into one, right? So how do I account for that?
You double it probably?
Why double it? Like let's say it cost me A amount to merge all of these into one slime, and it cost me B to merge all of these into one, and then maybe the current size of the slime is X and the current size of the slime is Y. Then you said the cost will be A plus B.
Oh yeah, plus x plus y.
Yeah, exactly. Okay, and then X plus Y is actually just the sum of the entire subarray, because no matter what order we merge the slimes in, the total size will always be the same. Yeah, so that is in fact exactly the formula I had already written on the slides. dp from L to R is the minimum across like all of the different midpoints M, where like L is less than M and less than R. Yeah, I think that's correct. Of like dplm plus dpmr plus the sum of the array from L to R. Okay. And then the base case that we will have is that the cost of any subarray of length 1 is just 0, because obviously if you have like one slime by itself, it's already merged into one slime, there's no cost to be paid. And then as for actually how to compute all of these states, we need to make sure to like iterate in an order such that each state only depends on like a previous state that we have already computed earlier. So the way we will do that is we will start with the shortest intervals and then go to the longer intervals. Because all of each interval will only depend on shorter intervals than it. So first we will do all the intervals of length 1, which I call the base case, and all the intervals of length 2, and then length 3, and so on. Okay, yeah, so this is like the transition example, which is kind of similar to what I do on the board. If we want to compute the dp value of the entire array, which is the cost of merging all of it, we just like iterate through all possible midpoints and pick the smallest one. And then at the end we also add to it the sum of the array. So in this specific case, I think the smallest sum would be this one, because that sums to 42. Well, this one is 45, that one is 46, and this one is 60. Yeah, so we would do like 42 plus whatever the sum of the whole thing is. Okay, and then so here is my implementation for the problem. So the way I implement this problem, first I just have like a constant for a really big number, which I call like infinity. I just set that to like 10 to the 18, because the specific problem I implemented, which will be on the problem set, basically says that like all the slimes have size at most like 10 to the 14 or something, and I concluded that the maximum answer will be never more than that. And then I define my dp table, Initially, I initialize that with all the infinities, although I don't think that's actually too necessary because I like recompute everything anyways. So first I do all of the base cases where I set all of the intervals of length 1 to have like a dp value of 0. And then I do my iterations in like increasing order of array length. So I start with the arrays of length 2, and I go all the way up to arrays of length n. And then for each one, I iterate through all possible left endpoints, such that you can have like an array of that length starting at that left endpoint. And then for each of those, I iterate through all of like the possible mid values, and I find the one that gives me like the best split. And finally, at the end, I add the sum of the relevant subarray, and then I print the answer. So can someone tell me what is the time complexity of this program? So the only input parameter is that the array has length n. Or does anyone have any questions about my implementations or the solution idea in general? Okay. Wait, is your hand up? No? Okay. Okay, so for the time complexity, first, can someone tell me how many different states there are in my dynamic program, which is also happens to be like how much memory I use?
Oh, that's correct.
Yes, that is correct. I have O of n squared states because there are like well, in reality, there are like only roughly n choose 2 subarrays, which is only like n squared over 2. But the way I define my dk table is I just store all n squared possible of them so that the indexing is more convenient. Okay, so I have n squared states, and then how long does it take for me to compute the value of one specific state? Yes? Yeah, basically. If I have a state where like it represents a subarray of length size or like r minus l, then it will be only r minus l, which can be at most n. So we can definitely conclude that the time complexity of our algorithm is at most O of n cubed, because I have n squared states and I do at most n work for each state for like iterating through all the possible midpoints and summing the array. Summing the array could be done a bit more efficiently, for example, if I use a prefix sum array, but that doesn't matter because it doesn't affect the complexity because I do like O of n work for iterating anyways. Technically, this doesn't prove that our algorithm is actually like exactly n cubed, because it could be possible, since this is often less than n, it sums to a smaller value. But I think if you do some math and like actually calculate it more precisely by calculating like how many arrays of length 1 there are, how many arrays of length 2 there are, and so on, you do get that it's unfortunately not faster than n cubed. Okay. Any questions about this specific problem about merging slimes? Yeah?
Why is, like, if you have, instead of splitting the arrays like two sections like L, M, M, R, like, how do you prove that, let's say you take the first element and the last element and then the middle range?
Yes?
Like, why is that? And you merge all the first and last ones first.
Your question is, why is that always optimal?
Or like, why is it always like contiguous subarrays?
Well, it's always contiguous subarrays because the problem statement says that we always merge adjacent slimes, and the slimes never change their order. So like if we have one slime that was merged from different slimes, it must have been a contiguous set of slimes, otherwise they would not have been adjacent and you can't merge them. Yes?
Is it possible to solve this problem without dynamic programming, like faster?
I think this. I don't know of a faster solution. I think there is some problem that's somewhat similar to this that has a lot more complicated solution that ends up being faster than dynamic programming, but I don't know if that's for this specific problem. I can maybe look into what I'm thinking of after the lecture. Okay. Any other questions about this problem? Okay, so let's just summarize what we learned today. So dynamic programming is this technique where you split a problem into different smaller identical subproblems that you can solve, and you store the values for those problems so that you can reuse them to avoid doing repeated calculations. So dynamic programming is quite a general technique, and I guess you should use it whenever you can, whenever you can write your problem in a way such that it naturally requires you to store different things to avoid computing things repeatedly. That's just yeah. Okay. Thank you for coming to today's lecture. Here's the attendance form, and tomorrow we will have some more advanced dynamic programming techniques. The contest, let's say the contest will be released in 5 minutes at exactly 5. I think that we can wait that long. That's fine, right?
You already released it.
Oh, okay, never mind then. Anyone have any questions about anything today? Maybe any of the earlier problems? No? Okay, thank you for listening.